Hi, today I'd like to talk about work I've been doing to address uncertainty in the coupled system. Um, and I'd like to talk about the sources of uncertainty in the coupled system. And first of all, when I'm saying coupled system, I am referring to the ocean and atmospheric system. There's previous work on air-land interactions that I'm not going to present here. So I'd like to break up the uncertainty into the different components of the system. So in the atmosphere, our sources of uncertainty come to unresolved processes that we resolve through estimate through physical parameterization such as moist physics, radiation, and turbulence. And there's also uncertainty in the model due to unresolved scales in the dynamics that can be associated with the finite differencing in space and time that then has these scales, these unresolved processes um, affect on a mean flow. Additionally, there's uncertainty in the fluxes coming from the lower boundary, either it be land or ocean, and some of this uncertainty is due to subgrid scale variability, and that could be either in the surface type, such as the surface roughness of waves in the ocean, errors in clouds that will affect the shortwave and long-wave radiative heating, gustiness, various things in the surface. And in the ocean, there's vertical mixing is parameterized, and also just like in the atmosphere, there's dynamics, and in the ocean, since the Rossby radius of deformation is much shorter than the ocean, there's a lot more unresolved scales than in the atmosphere. And specifically, the resolutions that we're running at in this study, mainly 1 degree and a quarter degree, doesn't resolve eddies properly. And also, the one unique thing about the ocean that we don't have in the atmosphere is uncertainty in the equation of state. So, density has a temperature and salinity dependence that is not linear, and it's actually not exactly known, and is parameterized. And just like in the atmosphere, the surface fluxes are uncertain and cause errors in the motion. So, how do we address this uncertainty? And I've presented this many times before. For in the atmosphere, we represent the uncertainty in the physical parameterizations through SPPT, or um, more properly called the stochastically perturbed physical tendencies. Um, and the model dynamics is addressed through SCEB, or stochastic kinetic energy backscatter. And in a hand wavy sense, the surface flux uncertainty is addressed through SPPT and the SHUM, or specific humidity perturbations, which applies perturbations to the lowest levels, model specific humidity, to at least account for subgrid scale variability in the humidity field. And then for the ocean, there's different ways to address uncertainty and vertical mixing. And two things that I will present here are basically perturbations that you could do to the energetic boundary layer, and an ocean version of SPPT. And then there's other ways which I haven't worked on to basically work on uncertainty and dynamics, is to implement a SCEB for the ocean. And there's also Ghent McWilliams parameterization that you can apply perturbations, and the GM scheme is intended to parameterize unresolved eddies. And in addition, there's work out there working on a stochastic equation of state to address the uncertainty in the equation of state. And the surface flux is also the SPPT scheme will capture some of the uncertainty in the surface fluxes. So, getting more detail on the ocean stochastic physics that I have implemented in the unified forecast system is based on the um, work done in the Zuricki et al. Paper in 2017, where there's energetic planetary boundary layer perturbation and an ocean SPPT. So for the EPBL scheme, there are random perturbations to the kinetic energy generation and dissipation terms. And these random values are perturbed independently, so one for the production, one for dissipation, with a AR1 process that's correlated in space and time, just like I have typically done for SPPT and SCEB. And then the ocean SPPT is done in basically the same way as in the atmosphere, where the tendency after your column physics is a random number times the difference of the state before and after physics divided by the time step. And one thing I want to note in MOM6 there is time step splitting, so only the temperature and salinity and the layer thickness are actually available to perturb the momentum equations, and physical processes that affect that are done in a totally separate part of the code, and I have not implemented anything in that side of the code yet. So the experiments I want to show here to look at our initial testing of the ocean stochastic physics are a simplified version of the coupled system, where I am running an ocean and ice model forced with reanalysis. So this is called the data atmosphere configuration of the Unified Forecast System, which consists of a MOM6 ocean and a CIC6 model, ice model. And for presentation here, I'm showing two different initialization. One is a northern summer case of August 1st, 2014, and one is a northern winter case of January 1st, 2016. And I'm comparing two of the resolutions. So one is nominally 1 degree, and which is the development version that I have been testing because it's a lot cheaper. And then the quarter degree is the target resolution for operations. So I want to compare the two to see if any information can be transferred. And what I've done is on 30-day runs with no initial condition perturbations, and only stochastic physics will provide ensemble perturbations during the integration. And I've done 10 realizations for each of these experiments with different random walks for stochastic processes. And I've tested the EPBL scheme and the SPPT individually. So first I'm going to show the maps of sea surface height spread, and spread I mean standard deviation, for different the different stochastic physics and then different lead times. So to get you familiar with the plots I'm showing here, this is a sea surface height spread in centimeters for the first day of the forecast for just the EPBL perturbations. Top row is the August case of northern summer. Bottom row is January 16, which would be northern winter. Left column is the 1 degree model. Right column is the quarter degree model, and this will be repeated on the next series of slides. So the thing I want to point out here is in the 1 degree model you see more spread, colored by these darker colors here, along the coastlines and specifically in the Gulf of Mexico, that you don't see in the quarter degree model. And this might be to initialization shocks, because what I'm doing is I'm starting the model off with a quarter degree initial condition that I interpolate to 1 degree. So it's possible that some of this spread here on the coastlines is just noise that is being excited, and maybe is propagating at different speeds based on slightly different ocean conditions. I have not looked into that yet. But the thing I do want to point out that is consistent is in this EPL schemes that you actually do see ensemble spread growth in the equatorial Pacific Ocean, mainly in the summer case in the cold tongue ranges, and you see this little stripe of spread. And to compare this to the SPPT, and first of all you see a much darker colors. And also I want to note that this scale is actually twice the range as the previous one. So the SPPT perturbations are doing much more spread growth compared to EPBL scheme. But the thing I want to point out is that it's very uniform globally away from these coastlines, which again might be just noise coming from the initialization. So you're not seeing anything really project onto the equatorial cold tongue or anywhere else. But then when you got to day 30, now we're back at the EPBL perturbations, you do see spread generation in the cold tongue region. In the August case, you see it in both the resolutions. You see more spread in the 1 degree resolution in the cold tongue region, and then in this general South Pacific area and into the Indian Ocean, you see more spread than in the quarter degree model. In the northern winter case, again, there's more spread in the 1 degree model in those areas compared to the 1 degree, but it's not as dramatic. The thing I do also want to point out is, and this is the difference of the resolutions, in the quarter degree model, you are seeing changes or ensemble spread in the western boundary currents, such as the Gulf Stream, the Kuroshio, and this zone here that is sort of between the Southern Ocean and Southern Indian Ocean that is very active in the quarter degree model and not so much in the 1 degree model. Then if you go to the SPPT, again, the rain, there's, in this case, the color bar is the same, but the again, there's more spread growth due to SPPT, and it's not as obviously uniform as in the 1 day forecast because I guess the dynamics are carrying along this information and growing it in these sensitive areas. But here you actually are starting to see at least some spread in the western boundary currents in the winter case at 1 degree. So now looking at sea surface temperature, you see here it is actually in the day 1, you don't see really any difference between 1 degree and a quarter degree. Very similar. You're getting spread growth along the cold tongue and then in the summer hemisphere. And that's the same case in the January case. It's the southern hemisphere is dominated by this spread, which is not too surprising because that the mixed layer is much more shallow in the summer, so it could change quicker. And then looking at SPPT, it's actually again favored to the summer hemisphere, but you are seeing spread growth in the winter hemisphere. Specifically, here you can see in the Kuroshio extension of Gulf Stream, you're seeing even day 1 changes to the sea surface temperature. And then if you go out 30 days, here you're starting to see differences between the resolutions. It's similar to the SSH where you're getting this increased spread in the southern subtropical oceans of the Indian and Pacific Ocean that you don't see in the quarter degree model. But other than that, there's really not major differences. So there's not a strong sensitivity to resolution in general, just a regional sensitivity for this metric. And then going to SPPT, similar story. It's stronger. It's the same regional dependence of the Southern Ocean here. Actually, the Kuroshio extension slightly stronger in the 1 degree model than the quarter degree model. And all in all, there's not a big difference here. If I plotted a time series, which I'm not showing here, if you average over the regions, there is more spread growth in the 1 degree model, but I think it's due to certain regions. So the summary of the forced ocean runs is that the 1 degree model has a tendency to be more sensitive to ocean stochastic physics in certain regions. Some areas not so much. But the SPPT has a stronger impact on both sea surface temperature and sea surface height spread. But SPPT seems to eject spread more uniformly over the globe, while the EPBL perturbations seem to be a little more focused in the dynamically active regions. So that's something we could possibly use in a tuning sense if needed. And then I want to move on to a fully coupled model in a more realistic case where I'm looking at ensemble spread growth with real uncertainty in the initial conditions, and also comparing to looking at the ocean in stochastic physics and comparing it to the atmospheric stochastic physics. So what I'm going to show here are results from the 1 degree version of the UFS, which contains a C96, or roughly a 1 degree GFS atmosphere, and 1 degree ocean and ice models. And for the atmospheric initial conditions, I have GFS ENKF perturbations from the GEFS reanalysis. And then for the ocean, I created perturbations by taking differences between 4 different ocean reanalysis products and then adding them to the EMC's MOM6 initial conditions, which are obtained from doing a 3D variational simulation of observations in a forced ocean run. And here I have listed the different reanalysis products that I'm differencing. And then I'm also taking a single ice initial condition from the CPC ice analysis. So I do not have ice ensemble initial conditions. And then the experiment setup here I'm going to show here is just for one case. All I have is January 1st of 2012, because it's very tedious to download all these different reanalysis products. But I have a 10-member ensemble. And then my first experiment is just a control run where I only use no stochastic physics, only initial condition perturbations. And then I have a set of runs that are called atmospheric stochastic, which is using SPPT and SCEB in the atmosphere, and these are based on the operational configuration. So SPPT has 5 different random patterns of different length and time scales. And then the new runs, the new runs in the ocean are for basically using the ocean stochastics. So I'm actually combining the EPBL and the SPPT schemes that I shown in the previous section together. So they're both active. And then I do runs where basically both the atmosphere and the ocean are turned on. So what I want to show is results from this one set of ensemble forecasts that goes out for 35 days. So first on the left panel, I'm showing the sea surface spread average 60 south to 60 north. I'm trying to avoid the sea ice areas since I have not initialized an ensemble of ice. On the right side is showing the spread of next layer depth for that same region, 60 south to 60 north. First I want to show you so the black line is the ensemble spread from just initial condition perturbations, and there's a little bit of initialization shock, but then it grows throughout the 35 days. The red line is ensemble spread of the ensemble, which includes the atmospheric stochastic physics, and over the first 3 days is indistinguishable from initial condition perturbations, but then the atmospheric perturbations are starting to affect the sea surface temperature, and you see an increase in spread over the next couple weeks. But then by week 3, they're indistinguishable. The green line is ocean stochastic physics. So you see right from day 1, there's a boost in spread from stochastic physics, but that boost sort of fades out over time, and again by week 3, there's no difference from the control. So, but when you add both the stochastic physics, atmospheric and ocean stochastic physics, you see a boost in spread that actually stays above the control a little longer. But again, it does cross over into the indistinguishable from control by like day 25 or so. In mixed layer depth, you see actually it more uniform, the progression that the atmospheric stochastic physics does a little bit, ocean does more. Combining them gives you a boost that goes out the full 35 days. But you can see that there's initialization issues, that my initial spread is much bigger than where the model wants to be. And to really reaffirm that, so to really show you a problem with my initial ensemble is showing you the spread of the zonal current 200 meters below the surface, where you can see the initial condition ensemble spread is about 6 centimeters per second, and the spread collapses down to about 3 centimeters per second by day 35, and stochastic physics doesn't really do anything. So this sort of really suggests that my initial conditions by just differencing the different analyses is not a proper method to address the initial condition uncertainty. So switching over to looking at maps of the changes of spread, what I'm plotting here is the difference of the ensemble spread of sea surface temperature of 3 stochastic experiments against the control. So top left is atmospheric stochastic physics, top right is ocean stochastic physics, and then the bottom left is when I have both the atmosphere and ocean stochastic physics on. And what I'm showing here is, that's again an SST spread for day 7. Where you see in the ocean stochastic physics, you see a general increase in spread throughout the southern hemisphere. Again, this is a January initialization, so this is the summer hemisphere where you expect to see more spread. And you see a little bit of spread, but it's mixed blues and reds in the atmosphere only. And if I plotted earlier, like day 1, day 2, the atmospheric stochastic physics would show no spread and all the ocean stochastic physics, and then the coupled one looks like the ocean. So that's why I'm not showing that. And if I plot beyond this, like day 20 or so, in a map sense, you're not going to see any difference between any of these runs. That there's just, there's positives and negatives, and unless you make an area average, you're not going to see any systematic difference.
If we look at a similar plot for mixed layer depth, in this case you see a more uniform increase in spread in the ocean stochastic physics on the top right than you do in the atmospheric stochastic physics on the top left, but you do see there is a net positive in the atmospheric only. And then when you combine the two, you do actually, you still get a more increase than in the ocean stochastic physics, again, which is consistent with the line plots. So in conclusion, there are 2 ocean stochastic physics schemes that are now implemented in the unified forecast system. Overall, the 1 degree ocean model is more sensitive to ocean stochastic physics, but the quarter degree model does have a stronger sensitivity in the western boundary currents in the Southern Ocean. And looking at the coupled forecasts, the ensemble shows that ocean stochastic physics consistently increases spread over the control ensemble for only the first 2 weeks for sea surface temperature, but longer for mixed layer depth. And adding in the atmospheric stochastic physics complements the ocean stochastic physics. And everything I showed here is very ocean related. And I didn't show anything in the atmosphere because ocean stochastic physics does not impact the atmospheric variables such as Z500 or U850 or precipitation. So I didn't bother showing it. So the outstanding issues that I'd like to perhaps discuss when we talk about this next week is that I need to perturb roughness lengths in the flux calculations to address the consistency of flux perturbations between the atmosphere and the ocean. And are there a better way to perturb the fluxes than the roughness lengths? And this is what I'd love to hear from the audience. And the other thing I want to point out is that the Ghent-Williams scheme, which parameterizes the subsquid scale eddies in the ocean, is not active in the quarter degree model. But does it make sense for me to actually use the GM scheme to still produce a tendency that I could then perturb to modify the flow or the thicknesses in the quarter degree model, even though it's not active deterministically? And then the other thing is it worth perturbing the ocean currents with the SPPT, and should I implement SCAB in the ocean? So thank you for your time. I'm looking forward to answering any questions. Thank you.